We're going to continue to look at two quantitative variables, and in this lesson we're going to take a look more at linear regression. So let's consider crickets and temperature. Can you estimate the temperature on a summer evening just by listening to the crickets? Well, I would say based on this scatter plot of two categorical or quantitative variables, I would say we probably could. We have our explanatory variable on the horizontal axis. We have our response variable on the vertical axis. So as we look at this, we need to try to find a line that kind of goes through the middle of all of our data and best describes our data. Oops, that was kind of fast. Sorry about that. And it would look about like this. Now, the equation of a line can always be written in this form of a plus b times x, where x is your explanatory variable, and y hat is your predicted variable from your line. So x is your explanatory, y is the predicted response, and a and b are your slope and your y-intercept. Now, we want to use our regression line to predict what we're going to get for y for a given value of x. So if we look at a regression line for our chirps versus temperature, we would get this. So if we take 37.7 and add to it 0.32 times the number of chirps per minute, we're able to predict our temperature. So if you listen and you hear crickets chirping at 140 times per minute, we should be able to take 140 chirps per minute, put it right here, and calculate and estimate our temperature. So we're going to go 37.7 plus 0.23 times the chirps per minute, put that into our calculator, and we get 69.9 degrees Fahrenheit. So go ahead and try to figure out the predicted temperature for 103 chirps per minute. So we'll go 37.7 plus 0.23 times 103, and we get, oops, forgot something here. It's 61.39 degrees Fahrenheit. So how does this show up when we're looking at a graph? So if we're at 140, we can go straight up from 140 to our line. Once we get to our line, we want to go straight to the left. And wherever we would come out over here, that is our predicted temperature. And it looks like it's about 70 degrees. Now remember when we did it before with the equation, we had 69.9 degrees. So we can also just look at our graph. So try to figure this one out. If they're chirping at 180, what's the temperature? So we can go from 180 straight up and then straight over. And to me, it's just slightly less than 80 degrees. So I would say of our best answers, it's 80 degrees. One of the cases we had for 103 chirps per minute was 63.5 degrees Fahrenheit. So how far off was our predicted from the observed? When we did our predicted, we had 61.39 degrees Fahrenheit, where in reality our observed case for 103 was 63.5. If you take your observed minus your predicted, you would get 2.1. That's also referred to as your residual. With our line of best fit, we want to try to find the line that's going to best fit. But how do you do that? Well, you want to take a look at your observed values, you want to look at your predicted values, and you want to find a line that really minimizes those. So our observed value height is here. Our predicted height would be down here. So here's our observed value. Here's our predicted value. We want to look at the difference between those two, and that's referred to as our residual. Whenever you take the observed value minus the predicted value, or y minus y hat, that vertical distance that we were talking about, which in this case was 2.1, is your residual. Now, if your point was below, it would be a negative residual. Now, we want to make all these residuals as small as possible. So how do we do this? Well, it's called the least squares regression line. For the most part, you want to find all those residuals. You need to square them, you need to add them together, and you want to do it in a way that makes all those as small as possible. It's awful hard to do by hand, so we rely on technology to do this. And our least squares regression line or regression line are kind of used interchangeably. Most of the time we'll just refer to it as our regression line. Now, if you wanted, you could go ahead and take a look at that vertical distance, and then you could square it so it forms a square. Take a look at that vertical distance and square it, vertical distance and square it, and you want all of the sum of those squares to be as small as possible. But we're going to always be using technology to do that. Now, it can be done with StatKey. Underneath two quantitative variables in the left side, left-hand column of StatKey, two quantitative variables, we could look at, hit the drop-down menu and hit crickets, and then we could have it display the regression line, and then over here on the side you can see your slope and you can see your y-intercept. Your slope is your b value, your y-intercept is your a value. And so you would get this for our prediction, or predicted line, or our least squares regression line. Now, we could use Minitab or Fathom or R or even Jump, but either way, we get pretty much the same thing. Unlike with correlation, when we switched X and Y around, it didn't make a difference. With regression, it does make a big difference. So we had said when we were looking at chirps versus temperature, this was our regression line. If we were to switch it around and look at temperature versus chirps, we get a totally different slope and totally different y-intercept. So just be aware of that. Once again, b is your slope, a is your y-intercept. So b tells you how much your y is going to increase for each one increase in x, where a is your predicted value when x is 0. So here our slope was 0.23, which means as you increase, or as your chirps increase by 1, the temperature goes up on average 0.23 degrees Fahrenheit. This is our y-intercept, which is our temperature when we have no chirps. But is that really meaningful? None of our data had chirps getting anywhere close to our chirps being 0, so it's not really meaningful. So you do not want to use a regression line and look at values outside of the range of your data. You only want to look within the range of your data and use it to predict. You don't want to go outside. That's extrapolation. Now, if none of the values of x are anywhere near 0, then your y-intercept is meaningless. Is it needed to get the line in the correct spot and make correct predictions? Yes, but it doesn't have meaning in the context of the real world then. So as we think about the units, whatever the units of our y hat are, it matches with y. Now, a has to have the same units. However, our units of x are going to be something different. And our b value, our slope, is going to be the units of y over x. Remember from algebra, slope was y over x, so it's going to be the units of y over x. In the context of our chirps per minute and temperature with our crickets, our temperature is in degrees. Our 37.7 was also in degrees. Our chirps was chirps per minute, so our slope has to be the degrees over chirps per minute. It's always units of the y over units of the x. So computers will calculate your regression line between any two quantitative variables, even if they're not associated and even if it's not linear. Always plot your data and only do a least squares regression line if it's linear. If it's not linear, then don't use it. Outliers affect your regression line a lot. Always plot your data and look for outliers. So, answer this question. Pause the video and answer it. And in this case, we're going to say it's not A because we're not trying to predict your life expectancy on your birth rate. We're doing it the other way around. It's really neither, because it's not B because we're not dealing with a causality situation because it was not an experiment. Higher values of X may lead to higher predicted values, but it does not mean that one thing is causing the other. So it's not necessarily a causation situation. Causation can only be determined in a randomized experiment. So what happens if R is 0? If the correlation between X and Y is 0, what would be the regression line? Well, it would be meaningless, and it would just be a horizontal line of Y equaling a number with no X as an input, which makes sense because if it's just a bunch of scattered points, whatever you have for X has no effect on Y. The horizontal line is not affected at all by whatever X is. So in summary, we have our B being our slope, our A being our y-intercept, and we're trying to minimize all those residuals. Remember, a residual is your observed value minus your predicted value, but we're going to go ahead and use technology to find that least squares regression line. X is going to be your explanatory variable, while Y will be your response variable. Now, just make sure you don't go beyond the data to make predictions. Make predictions only within the range of your data. And look for outliers. And a strong linear relationship, no matter how strong, does not imply causation. And always plot your data.